In this module, we will introduce an approach to controller design. In the previous module, we gave a simple illustrative example of how to design a controller. In this module, we will try to be a little bit more rigorous. Specifically, we'll discuss how to generate requirements for a control system. Then we will introduce one particular approach to controller design, which is a pole placement approach. And finally, we'll introduce a controller structure that's the most prevalent in industry today, and that's the PID controller. So in general, engineers are familiar with the concept of developing requirements, quantifiable measures of whether or not the system performs to a certain level. With control requirements, there are typically specific types of requirements for control systems. Therefore, we must be able to take specifications on the larger system and translate them into specifications specifically on the control systems. For example, a vehicle may have a requirement on a 0 to 60 time, or something to do with passenger comfort, or different components may have a voltage rating or a current rating. And so we need to keep those in mind and translate those into controller specifications. Example specifications in terms of the transient performance of a control system often derive from the system's step response. So some of the things that we've discussed previously are things like time constant, which capture the speed of response of a system, in particular a first order system, overshoot, peak time, settle time, and rise time. And so these things capture sort of the speed of response of the system, as well as the amount of oscillation in the system and how quickly that oscillation damps out. Control systems often also have requirements on their steady state performance. For example, that the steady state error must be less than some amount for a particular type of input, a step input, a ramp input, or something more general. In order to test against this specification, we can apply the final value theorem for different types of reference inputs. And here is a reiteration of the final value theorem, in particular for error. Throughout the course of this semester, we've learned that the poles of a system or its transfer function are an indication of its time response, its natural response. So one approach to controller design is to try and design your controller, choose your control gains so that the poles of the closed loop system meet the given requirements. That is, give you a certain speed of response, give you a certain overshoot, things like that. If a system is simple, a canonical first order or a canonical second order system, then we have precise relationships between poles and the shape of the step response. For example, we have an exact equation that tells us how peak time relates to the imaginary part of a pole, or if it's a first order system, how the pole relates to the time constant. If a system is more complicated, it's not a canonical system. For example, if it's a higher order system, these requirements or these expressions that we've derived won't hold exactly. But one idea with a higher order system is to place one or two dominant poles to meet the requirements and place the rest of the poles to be significantly faster, so that we can, in essence, neglect the effect on the dynamics or on the transient response. Similarly, if a system has a 0, it's again not canonical and our relationships don't hold exactly. However, we can still approximate the system as a canonical system and use these relationships we've developed to give an indication of the effect of poles on response, even if they're not exactly right. They give an indication of trends. And seeing that a lot of times these canonical relationships don't hold exactly, this process will often be iterative. We can use the relationships to sort of determine should we make the gain bigger or larger, but in order to know for sure, we'll actually have to sort of test it out and then go back and modify the gains. We will now go ahead and go through a complete example of how to design a PI controller. In other words, how to choose the proportional gain Kp and the integral gain Ki for a first order plant, which is the same sort of plant that we looked at in the previous module. And so the first thing that we need to do in order to design our controller is to find the closed loop transfer function, and that will enable us to see what the effect of these control gains are on the closed loop poles, and hence the closed loop behavior. So looking at this, we have a sort of standard negative feedback system with an output of velocity for our cruise control system and an input of desired velocity. And since this has a standard form, we've memorized the rule for how to manipulate this block diagram into a single transfer function. And if you recall, that rule is forward over 1 plus loop. If we look at the forward path from our reference input to our output, there are two blocks, or sort of two subsystems in the forward path, the controller and the plant. And again, if you recall, if we have two transfer functions in series, they simply multiply. So we'll go ahead and multiply these two, but before we do that, I'll go ahead and rearrange this into a sort of a single fraction, or a single rational term. So I need to get a common denominator. This term has a denominator of s. In order to make this term have a denominator of s, I need to multiply and divide through by s. And so that will make this Kp times s, and then just plus Ki. And so since those two are in series, I multiply them. And so in the numerator, I'll get Kps plus Ki divided by s times the quantity ms plus b. And then our denominator is 1 plus loop, where in this case the loop is this, and it also only includes these two blocks. There's nothing, no dynamics in the feedback path. In essence, you could imagine that there's just a constant 1 in the feedback path. And so the loop is going to be exactly the same as the forward. So again, Kp times s plus Ki divided by s times the quantity ms plus b. So that completes our transfer function. That's the closed loop transfer function, but generally we like to rearrange it, clean it up a little bit. We'd like it to get it reduced to the form where we have a single polynomial divided by a single polynomial. In order to do that, we need to clear out these fractions. We need to clean up these denominators. So since the denominator of those two terms is equal, if we multiply by that expression in the numerator and the denominator, that'll clear out. So we multiply through by s times the quantity ms plus b. In the numerator, that'll cancel. This term will just be left with Kps plus Ki. When we do that in the denominator, it will also cancel this term, leave us with Kps plus I plus Ki. And then we also distribute to the plus 1. So that's our reduced transfer function. I'll take one further step and expand the denominator and combine like terms. So the numerator stays the same. I distribute that s. I get m times s squared. I distribute the s to the b. I'll have b times s. I also have this term Kp plus s. So I can factor out the s. And then I'm just left with this Ki. So this is the resulting closed loop transfer function. And we can see how the two control gains affect the coefficients of the polynomial in the denominator. Looking at the units of this transfer function, the input is a speed, the output is a speed. So in essence, the units will cancel and the transfer function will be unitless. Moving to the next slide, here again repeated is the transfer function we just found. If we look at this, the fact that we have two parameters, Kp and Ki, and we have a second order system, we have a system with two poles, we can see that we can in essence place the two poles anywhere we'd like. So we have sort of two knobs to tune, Kp and Ki, and two things that we're trying to achieve, or two things we're trying to place. And so sometimes this is called a 2-degree of freedom system, or a 2-degree of freedom controller. And so what we'd like to do now is to try and understand the effect of changing these control gains. And the way that we do that is by sort of matching this denominator to the canonical second order system denominator. So if we match the form of the denominator, a canonical second order system has a denominator of the form s squared plus 2 zeta omega ns plus omega n squared. We can match that to this denominator. In order to get the two to correspond, we need to rearrange this so that the leading coefficient is 1, because that's the form we have here. So in essence, we're going to divide through by m in the denominator. So if we do that, it'll cancel this m. Then we'll have b plus kp divided by m and ki divided by m. Looking at this, strictly speaking, this transfer function is not a canonical second order system because it has a 0. But employing what we know about canonical second order systems will be illustrative. It will help us sort of understand the trends of the effects of Kp and Ki, if not the exact effect of Kp and Ki. So matching these two polynomials, we can see that this set of parameters is equal to that. So we have that zeta times omega n, which we also call sigma, is equal to this quantity where we divide through by 2. So it's equal to b plus kp divided by 2m. And so right away we can see how kp will directly affect sigma, which is the real part of our poles. If we match these terms, we can see that omega n squared is equal to ki divided by m. If we take the square root of both sides, we get that the natural frequency is equal to the square root of ki divided by m. And so here we can see that the integral control gain directly affects omega n, the undamped natural frequency. Going a step further, in order to try and understand the effect of these gains, we can look at how the poles move in the complex plane, where the horizontal axis corresponds to the real part of the pole, the imaginary axis corresponds to the imaginary part of the pole. We'll presume we have some complex conjugate poles arbitrarily, and if we recall, sigma tells us the real part of the pole, and omega n is sort of the radius. It's how the distance of the pole from the origin. And so if we want to sort of understand the effect of increasing Kp while holding Ki constant, so increasing Kp will make sigma bigger. So increasing Kp but if we keep Ki constant, omega n will be constant. Okay, so right away we can see what the effect of that is. So sigma, if we look back to our canonical second order relationships, affects settling time. So if we increase sigma, that's going to make Ts get smaller. Okay. Omega n doesn't directly enter the relationships we focused on. It does enter into the rise time equation, but we didn't derive that one. But moving these poles will also affect other parameters. So it will also affect omega d, which is the imaginary part of the pole and which directly affects peak time. And it will also affect sigma, which affects overshoot. Not sigma, zeta. Okay, so if we look at this, sigma's getting larger. So as we increase Kp, sigma gets larger. So this is going to move to the left. But omega n stays constant because Ki is unchanged. That means that the radius will stay unchanged. So in essence, the pole is going to sort of move along a circle to the left and down. It's going to keep the same radius, but sigma is going to get larger and larger. As we do that, we can see that omega d decreases. And we can see that if omega t gets smaller, that means Tp is going to get larger. We'll also see that this beta is going to get smaller. And that corresponds to sigma getting larger. We can see that in a couple ways. So one, we saw it here in the picture that this beta gets smaller. When our poles are real, when our poles are on the real axis, we have no oscillation at all. So that's the most damping you can get. When our poles are on the imaginary axis, they're purely imaginary, they oscillate without decaying. So that's the least amount of damping we could have. And so that's one way to sort of remember what the effect of beta is. So big beta takes us closer to imaginary poles. Small beta takes us closer to real poles. We can also see, so here, that increasing Kp makes zeta times omega n larger, where omega n is constant because Ki is constant. So if this quantity is getting larger, but omega n is staying constant, that must mean zeta is getting larger. So we can also see it that way. Increasing the damping ratio will cause overshoot to decrease. So that gives us a sense of the effect of Kp. Let's also see what the effect of Ki is. So let's say we increase Ki while holding Kp constant. And so what that's going to do, so if Kp is constant, that means that sigma is going to stay constant. And we know sigma affects settle time. So our settle time is unchanged. But omega n is going to increase. So as we increase ki, we're going to increase omega n. So we're going to stay on this line, this vertical line, with the same sigma, but the distance from the origin is going to get larger. So in essence, the poles are going to move up this line. So same sigma, same real part, but larger omega n. That also means that omega d will increase. And if omega d increases, that means that Tp will decrease. And it also means that as we go up, beta will increase. It means we're getting closer to the imaginary axis. So that means zeta is getting smaller. We can also see that here. So sigma is constant because Kp is constant, but omega n is getting larger because Ki is getting larger. So if this quantity is constant and omega n is getting bigger, that means zeta must be getting smaller. And a smaller zeta means more overshoot. And so that gives us a sense of what the effect of these control gains are. And again, these relationships don't hold precisely, or these relationships, I should say, don't hold precisely because we don't have a canonical second order system. But understanding these relationships help us get an idea of trends. It helps us, these sorts of trends of increasing Kp makes Ts smaller, or increasing Ki makes Tp smaller, those sorts of trends tend to hold, even when we don't have a perfectly canonical system. And so it can be helpful in tuning gains. At this point, we'll now go ahead and try and pick specific values of Kp and Ki to achieve two requirements. One being that the settling time equals 2 seconds, another that the peak time equals 1 second. And we'll go ahead and put in some numbers to make the calculations easier. So this is the closed-loop transfer function we were working with earlier. On the previous slide, we sort of saw the general effects of changing Kp and Ki. Now we're going to try and pick specific values. So looking at our system, matching it to the canonical sort of second order form, we're going to have a denominator s squared plus 2 zeta omega ns plus omega n squared. And our transfer function, once I substitute in values, will have 1 divided by m, which is 5. Have a numerator of kps plus ki, and then a denominator of s squared plus b plus kp, where b is equal to 1 divided by m, where m is equal to 5 times s, plus ki divided by m, where m is again 5. And so looking at our requirements, we want a settling time equal to 2 seconds. So thinking back to our relationships, we want 2s equal to 2. This relationship only holds for canonical second order systems, which we don't have because of this 0. But these calculations will serve as a good starting point for our tuning. So if I solve for sigma, I can multiply sigma to the right hand side, divide through by 2. I get that sigma equals 4 divided by 2. So we desire that sigma equals 2. recalling that sigma is equal to zeta times omega n, we can see that sigma, that coefficient, is going to be affected by Kp. So if we match those two, if we match the coefficients, we have that sigma is equal to 1 plus Kp divided by 2 times 5. So in essence, these two are equal. To isolate the sigma, the zeta times omega n, we divide through by 2. And it's desired that this equals 2. Then we can simply solve for Kp. So we have 2 on the right hand side, we can multiply through by 10. And then to get Kp by itself, we subtract 1 from both sides. We get that Kp is equal to 19. Or at least that's a good starting point for a choice of Kp. We can do a similar sort of thing for our other requirement, that the peak time equal 1 second. So the relationship for peak time is that Tp equals pi over omega d. We want that to equal 1. So if we solve for omega d, take this omega d, multiply it to the right hand side, divide through by 1, we get that omega d is equal to pi. Since we've already chosen Kp, essentially, we now want to choose Ki. So we look at the coefficients again. And we have that omega n is equal to the square root of Ki divided by 5. So this doesn't depend directly on omega d, which we've calculated, or sigma, which we've calculated, but we can determine the desired omega n based on this omega d and this sigma. So I'll go ahead and go to the next slide to give us some more room. Here again is our transfer function. And we've got that Kp is equal to 19. We've got that sigma is equal to 2. That omega d is equal to pi. And we have that omega n is equal to the square root of Ki divided by 5. So one way to relate these guys is we can recall that omega d is equal to omega n times the square root of 1 minus zeta squared. Or we can use geometry. So if we think back to what all of this means in the complex S-plane, we have that sigma is 2, and we have that omega d, the imaginary part, is pi. So in essence, we want to place our pole right there. And omega n is the radius, and we can essentially treat this as a right triangle where omega n is the hypotenuse, sigma is one leg of the triangle, and pi is the other leg of the triangle. So omega n is equal to the square root of 2 squared plus pi squared. If we type that into our calculator, that works out to be approximately 3.72 radians per second are the units. And so that means that we want 3.72 to approximately equal Ki divided by 5. In order to solve for Ki, we can square both sides. Square both sides to get rid of the square root. Then multiply through by 5 to get Ki by itself, and we get Ki is approximately equal to 69.3. Okay. So those are our two choices, at least initially, for our control gains. Kp equals 19 gives us the settle time we desire, and Ki equals 69.3 gives us the peak time we desire. So now the question is, will the closed loop system with this controller actually have a settling time of 2 seconds and a peak time of 1 second? And the answer is, of course, that it won't. And the reason it won't is because we don't have a canonical system, because we have this 0. So these relationships that we've been using for TS and TP, they rely on the system being a canonical second order system. The fact that ours isn't means that these two gains won't give us exactly the settle time and peak time we were shooting for. That being said, these will still be good starting points. The fact that we have this 0, how do you think it's going to change our actual behavior as compared to what's predicted? Do you think the settling time would be larger or smaller than 2 seconds? Do you think the peak time would be larger or smaller than 1 second? What do you think? So if you recall, the presence of a 0 tends to increase overshoot and decrease peak time, or make the system faster. So smaller TP than predicted, probably less than a second. And MP will be larger than predicted. This makes, well, so we can, with a decent amount of confidence, predict that the peak time will be less than 1 second. What the settling time is, that's a little harder to predict, because the system will be faster, but it'll overshoot more, it'll oscillate more, and so these tend to sort of work in opposite directions in terms of their effect on settling time. So we may not be precisely sure what the settling time will be, whether it will be larger or smaller than 2 seconds. That being said, if we did apply these gains and look at the results, we can go back to the analysis we did a few slides ago and use those trends to help us tune Ki and Kp. How would we change them to make TP larger, to make MP smaller, etc.? So as we were just stating, if the system is not canonical, if it has a 0 or more poles, we can use these calculations based on the canonical system as a starting point. If the system is higher order, has more than 2 poles, one thing that we can do is we can place 1 or 2 of the poles at the desired location and then place the other poles to be much faster, farther to the left, so that those 1 or 2 poles at the desired location dominate, and we can neglect the effect of the faster poles on the transient response. In that previous example, we were shooting for a settling time of exactly 2 seconds and a peak time of exactly 1 second, but in general, requirements are often given as inequalities. It's generally not required that the settling time be exactly 2 seconds. It's generally the case that the settling time be less than 2 seconds. So in order to examine this concept, let's try and plot the region in the complex plane where the poles of a canonical second order system must be located in order to achieve a settling time not equal to 2 seconds, but less than 2 seconds, and a peak time not equal to 1 second, but less than 1 second. So using the same relationships, settling time is 4 divided by sigma. We want it to be less than 2. We can multiply this sigma to the right hand side. So on that side of the greater than or equal sign, divide through by the 2, we get that we desire sigma to be greater than or equal to 2. Similarly, for the peak time, we have the expression that peak time is pi over omega d. We want that to be less than 1 second. We multiply omega d to the right, and we get that omega d. We desire omega d to be greater than pi. So in terms of the complex plane, where again the horizontal is the real, the vertical is the imaginary, sigma corresponds to the real part of the pole, and omega d corresponds to the imaginary part of the pole. We want sigma to be greater than 2, so that means we want to be to the left of this vertical line. Faster is farther to the left, and we want omega d to be greater than pi, so that means we want to be above this horizontal line. So if we had complex poles for a canonical second order system, we would want one of our poles to be located in this section. Since complex poles always come in conjugate pairs, that means that we will also want a pole in the region reflected across the horizontal axis. So complex conjugates always have the same real part but opposite imaginary part, minus sigma plus or minus j omega d. So these two regions identify where we would place the poles if we had a canonical second order system. Okay. So far we've discussed the effect of Kp and Ki on the transient response of our system. We may also want to design them to achieve a certain steady state behavior. So let's say that we want to know what is the resulting steady state error for a unit ramp reference. Okay, so plugging in our numbers, 5 for M and 1 for B, and plugging in the Kp we calculated and the Ki we calculated, this is the closed loop system we've designed for so far. We can calculate error from the fact that error is the difference between sort of what's commanded or what's desired and what we're actually achieving. In this case, since our output is V and we have a unity feedback system, E, the error, is that signal in our transfer function. So one way to calculate the error is to define a transfer function with an output of error and a reference input. So looking at this, we again have a unity feedback system. Forward over 1 plus loop is the rule for reducing a negative feedback system. If V desired is our reference and E is our output, and we look at the forward path from that input to that output, you'll see there's basically nothing in the path. So our forward path is in essence just 1. And then our loop includes these two blocks. So the forward path is 1, that's in the numerator. The denominator is 1 plus loop, where the loop is just the product of these two transfer functions. We get 19s plus 69.3 divided by s times the quantity 5s plus 1. Cleaning it up into the form of a single polynomial in the numerator and a single polynomial in the denominator, we can multiply through on the top and the bottom by s times the quantity 5s plus 1. We multiply that by the numerator, we just get a numerator of s times 5s plus 1. In the denominator, we'll cancel that term. We'll just be left with 19s plus 69.3. And then when we distribute to the 1, we'll also have this. So this is the transfer function for an input of v desired and an output of error. We can then find the steady state error by applying the final value theorem. So E steady state is equal to the limit as s approaches 0 of s times E of s repeating that. So E of s divided by v desired is equal to this. So to get an expression for E of s, we just multiply the transfer function by the input v desired. So we have this transfer function and we multiply it by v desired, where we have a unit ramp reference. And if you recall, the transfer function, the Laplace transform of a unit ramp, is 1 over s squared. So that's what we'll multiply through here with. So looking at this, we have s times E of s, where E of s is the transfer function times the input. This s squared, one of the s's will cancel with that s, one of the s's will cancel with that s. We're left with this. If you found the poles of this transfer function, they have a negative real part, so the final value theorem holds. This function is defined at s equals 0, so we can simply sub in s equals 0. If we sub in 0 for s, that'll go away. We'll just be left with a 1 in the numerator. You substitute 0 here, that term will go to 0. You substitute 0 here, that will go to 0. We'll just be left with 69.3, which is approximately 0.0144. So that is the steady state error for a unit ramp command in desired velocity. Looking at this, how might we decrease the error? How could we choose our control gains to make the steady state error smaller? Looking at this, you may recognize the 69.3 as the value of Ki that we calculated. So by making Ki larger, we make this quantity smaller, we decrease the steady state error. The proportional gain doesn't appear to affect the steady state error at all. If we had sort of a condition on steady state error that conflicted with the condition on the peak time or the settling time, we may have to iterate in the design of our controller, trying to sort of push back and forth between the various requirements. In the previous example, we designed a PI controller. At this point, I now want to discuss more generally the notion of PID control. Here's the transfer function of a PID controller. It has 3 terms, where in essence the input is the error, the difference between the commanded reference and the actual output, and what the controller produces is a control input into the plant. And so if you bring the error over, you can see that the controller output is a constant times the error, which is the proportional part. This multiplication of s with the error, which gives you differentiation, so part of it is proportional to the derivative of the error, and then another part takes the error and divides it by s, which is equivalent to integration in the time domain, and multiplies it again by a constant. And so this part of the control is proportional to the integral of the error. This type of controller is very widely used in industry. I've heard people throw out numbers like 90% of all controllers used in industry are PID controllers. I don't know if that's quite correct, but they are very commonly used. And one reason that they're commonly used is they're very intuitive and easy to implement. Everybody understands what a derivative is, everybody understands what integration is, so they can understand the concept of the controller and they can implement it. Despite its simplicity, it's also relatively sophisticated in the sense that the control command isn't based only on the current error, which would be the part that's proportional to the current error, but it also depends on the history of the error, i.e. the integral of the error, and the anticipated future error, i.e. the derivative of the error. And so those notions might not make a ton of sense quite yet, but we will try and sort of delve into the PID controller a little bit more and build some intuition. The way that we're specifically going to build some intuition is we're going to look at the effect of the three terms of a PID controller, the P term, the D term, and the I term, in terms of its effect on a canonical second order plant. And so here's the transfer function for our plant or our process which we wish to control. If we found the closed loop transfer function, it has the form forward over 1 plus loop, again because it's a negative feedback system where the forward path from R to Y includes just C times P, and then you have 1 plus loop where the loop again only includes C times P. Rearranging, so substituting in for P of S and cleaning it up, this is the form of the closed loop transfer function, where C of S is the controller and A and B are properties of the plant. So here again is the closed loop transfer function. The first type of controller we'll look at is simply P control. So of the three terms, it only has the P term. A P controller, the control effort is proportional to the amount of error. So that's where the name comes from. And basically what it says is the output of the controller is just some constant multiplied by the error. And so the bigger the error, the bigger the application of control. The smaller the error, the smaller the application of control. If we substitute this into our closed loop transfer function, this is the result. So looking at this, this has a form very similar to a canonical second order system. It has no zeros, it has only two poles, and so if we match these coefficients in the denominator of the closed loop transfer function, we can match them to the parameters of a canonical second order system, which we understand. So specifically, this term maps to omega n squared. Taking the square root of both sides, we have that omega n is equal to the square root of b times 1 plus kp. And then looking at this coefficient, we have 2 zeta omega n is equal to a. If we solve for zeta, we can divide through by 2 and omega n, where we already have this expression for omega n. And we find that. So a few things to notice is that increasing kp makes omega n larger. So you can sort of think of it as making the system stiffer. Increasing kp also makes this quantity smaller, therefore it makes zeta smaller. So we can think of this as making the system stiffer. We can also think of increasing kp as decreasing the damping. And these sorts of results are sort of intuitive. So by making the control effort proportional to the amount of error, if we increase kp, it'll react harder to a specific amount of error. So for a given amount of error, we get a given amount of control. We increase kp for that same amount of error, we're going to apply more control. So you can sort of imagine that the system would fight harder, push in one direction really hard the error changes sign, it pushes really hard in the other direction and it kind of rattles back and forth. So you can sort of imagine that it may overshoot more. You can imagine that maybe it'll oscillate with a higher frequency. Another thing that you'll notice is the fact that we have only one parameter Kp is we cannot set omega n and zeta independently. So if we choose Kp to give us some desired omega n, then we're going to end up with a specific zeta, which maybe is not the one that we want. So we only have one parameter, one knob to tune, so we can't set all of the parameters of a second order system independently. So that gives some intuition about the effect of P control on transient performance. Let's now look at the effect of P control on steady state performance. So again, we can find the steady state value by applying the final value theorem. So this is the final value theorem for an output y, the output of our closed loop system. Substituting in our transfer function. So this is our transfer function, and this is our input u of s, because we're doing a unit step reference. So this all together is y of s. The s from the input cancels the s from the final value theorem. Then this quantity has poles all in the left half plane because the coefficients of the denominator are all the same sign. This function is also defined at s equals 0, so we can solve the limit by simply subbing in for s equals 0. So we sub in 0 for s, that goes to 0, this goes to 0, and we're left with b times kp in the numerator and b times the quantity 1 plus kp in the denominator. That common factor of b cancels, and we end up with the final value of kp over 1 plus kp. So one thing that you'll notice is we've commanded a unit step reference. So we've essentially commanded the system with an input of 1. Yet the final value of our system does not go to 1. So you can sort of imagine a picture like this where you've commanded 1, but the steady state output approaches some value different than 1. So with P control, we will have some amount of steady state error for a unit step reference. Go ahead and take a second and think about what could we do with Kp in order to reduce the steady state error. In order to reduce the steady state error, we in essence want to bring this quantity closer to 1. We want our output closer to the commanded input. And we can make this closer to 1 by increasing the value of Kp. As Kp gets large, this Kp will dominate the 1. So we'll have a large number plus 1 divided into a large number. And so the bigger Kp gets, the closer this is to 1. So that gives us some intuition about how we can reduce the steady state error. Of course, by increasing Kp to reduce the steady state error, we may get some other adverse effects, such as we may increase the overshoot or the oscillation in the performance of the system. At this point, we'll now try and understand the effect of adding a derivative action to our controller. So adding derivative action to the P controller we were just looking at. Here again is our closed loop transfer function. So in this case, C of S will have a different form. In general, the addition of a derivative control allows us to anticipate the error. So if we're looking at how our error is changing with time, with proportional control, the control effort was proportional to the error. So in order to make the application of control larger, we needed the error to be larger. But with derivative control, we look at the slope, or the derivative. So even if the error is still relatively small, but it's sort of ramping up, that means that the applied control will also increase even before the error gets large. And so this is a quite a useful fact, and it in essence allows the system to have improved damping, because if the error is starting to take off, the control effort can work to combat it sort of early on. Something that we've discussed previously is the fact that differentiation can amplify noise. So we discussed this when we talked about signal processing and we were doing numerical differentiation of a noisy signal. And so this fact means that we should never use D control by itself. We should always use it in conjunction with proportional control, or proportional control and integral control. This fact also makes some people in industry hesitant to use derivative control in their controllers. Later in the course we'll discuss some methodologies for addressing this amplification of noise problem. So here's our controller. It has a constant that's proportional to the error, and then multiplication by S causes differentiation of the error, and another constant to make the control proportional to the derivative of the error. If we substitute it in to our closed loop controller and rearrange, this is the closed loop transfer function that we get. So looking at this, it's not a canonical second order system because of this 0. That being said, we can still use this transfer function to sort of build some insight. So we may not be able to predict the precise behavior of the system, but we can at least understand the trends in terms of the effect of increasing KD. Specifically, we can see that Kp, the proportional control, again affects omega n, just like it did when we had P control all by itself. And here we can see that Kd affects the sigma term, or the zeta omega n term. So if omega n is held constant, increasing Kd increases zeta. And this is sort of what we had just discussed, but it increases damping. Another way to sort of build intuition for this is if you think back to our discussion of dampers and dashpots, you may recall that the force generated by a dashpot is proportional to the velocity or relative velocities of the two ends of the dashpot. This is a similar case where the control is proportional to the derivative, just like velocity. If we went a step further and looked at the steady state behavior of this system, i.e. applied the final value theorem, took the limit as s approaches 0, this term would go away, this term would go away, this term would go away. So the effect of all the KDs would go away, and essentially we'd get the same behavior we got when we had just a proportional controller by itself. So the addition of the derivative action did not help our steady state error. Okay. One nice thing about this type of controller is that it's 2 degree of freedom, just like the PI controller we showed earlier with that earlier example. That is, we have a second order system with 2 poles, and we can place those 2 poles anywhere we'd like by tuning the Kp gain and the Kd gain. For example, one way that people often tune PD controllers is they first use Kp to increase the speed of the system and reduce the steady state error through its effect on omega n, and then they use Kd to bring down the overshoot through its effect on zeta. Now we will discuss the effect of adding integral control to our controller. So here again is our closed loop transfer function. With integral control, the control effort gets larger as the error is accumulated. So you can sort of imagine that the integral term is integrating the error. And so the longer the error goes for, the more the integral builds up, because an integrator is a summer. it calculates the area under the curve. So here's the form of a PI controller. We've got the term that's proportional to the error, just a constant. We divide by s to perform the integration and multiply by another constant. If we substitute that into our closed loop transfer function and rearrange, we get something of this form. Looking at this, it's definitely not canonical. Not only does it have a zero, but it's also third order. So it's a little more challenging to draw general conclusions about the effect of integral control. But it often tends to make the system slower and more oscillatory. And so one reason that is maybe you can imagine, is in order for the effect of the integrator to take hold, you need to sort of sum up the effect of the error. So if we can sort of imagine our error doing something like this, in order for the effect to build up, we need to add up the area under the curve. But if the error switches sign, then the sort of direction that the controller is pushing doesn't necessarily change sign. So we've built up this positive area. This will still be positive even when the error changes sign. And so what we have to do is we sort of have to unwind the integrator. We have to subtract all of this error off, subtract what's been built up in the integrator before we can start to push in the other direction. And so this can tend to make the system slower to react and can also tend to make it more oscillatory. Looking at the effect of integral action on steady state performance, we can again apply the final value theorem. So we take the limit as s approaches 0 of s times y of s, where y of s is the output of our closed loop system. This quantity here is the transfer function, y of s over r of s. We have a unit step reference, so this is our r of s. Taken together, we have our y of s. So the s from the input cancels the s from the theorem. We then can see again that we have a denominator where all of the coefficients are positive. Therefore, we will again have a system where the poles have negative real part. We can then solve this limit by simply substituting s equals 0, since the function is defined for s equals 0. So that goes away, that goes away, that goes away, that goes away, and we're left with b times ki divided by b times ki, which equals 1. And so what that means is, for a unit step reference, for a command of 1, the steady state value of our closed loop system will always approach 1. That means the steady state error is 0 for a step reference, which is a very useful thing. This tends to be the biggest benefit of using integral control, as it helps the steady state error. It's interesting to note that even if we use a very small ki, even if we don't use very much integral action, the steady state error will still go to 0. The thing is, it will just take a long time to get there. So the longer we integrate for, the bigger the control effort builds up, and eventually it builds up enough to offset the error. But if ki is quite small, that process may take a long time. To summarize, we've learned some intuition about the effect of the three terms of a PID controller by looking at a canonical second order system. Specifically, we saw that increasing Kp corresponds to making the control effort larger for the same amount of error. It tends to make the system faster, tends to reduce steady state error, but it can also make the system overshoot more. Increasing the derivative action allows the controller to anticipate an increase in error, thereby sort of damping the system. A drawback is that it can amplify noise. The addition of integral action tends to help reduce steady state error. But the fact that we have to wait for the integral to build up, and then when the error changes sign we have to wait for the integral to unwind, makes the response slower possibly. A caveat is that these guidelines do not hold for all situations. So this is sort of the intuition that we built for a canonical second order system. A lot of this intuition will hold for other systems, but it doesn't necessarily hold if we have a system that's not a canonical second order system, if it's higher order, if it has zeros. So specifically we need to actually dig into the mathematics, look at how the poles move around, look at how the zeros move around to actually understand the true effect of the control gains. For systems that are not canonical, we may need to use trial and error. And one approach is to try and look for a reduced order approximation. Try and identify if there are any poles that dominate the response. Try and identify if any of the zeros cancel with any of the poles. And so if we can take a higher order system and approximate it as a first or second order system, we can use some of this intuition. And this table here sort of summarizes what we were saying on the previous slide, but again, it's not always true. Okay, so if you recall, increasing Kp tends to help steady state error, tends to make the system faster, but it tends to cause more overshoot. The addition of derivative control didn't help the steady state error, but it tends to add damping and make the system settle quicker and have less overshoot. Integral control, the addition of integral control tends to help steady state error, but it may make the system slower or more oscillatory. So this brings us to the conclusion of Module 14. In this module, we introduced an approach to controller design. First, we discussed how to specify the requirements for a control system. In particular, we typically use parameters related to the step response of a system as its specification. Its settle time, its rise time, its overshoot, etc. We also introduced a pole placement approach to control. So the idea is that we interpret requirements in terms of pole location or transfer function parameters. So we have some specification in terms of speed, whether that be peak time or settle time, or we have some requirement on overshoot. And so we take those requirements and we translate them into pole locations, or more generally parameters related to pole location, like sigma, like omega d, etc. We then find the closed loop transfer function so that we can see how the gains affect the transfer function, how the gains affect the closed loop poles. And we solve for the gains to match the desired poles parameters. If this is a canonical system, then we're done, because we have exact relationships between the parameters and the time response. If it's not a canonical system, we can often use these relationships to sort of guide our tuning, but we will in general need to iterate in order to get the exact performance we desire. We then introduced PID control, which is one of the most prevalent controller structures found in industry, and we tried to build some intuition for the effect of the P term, which is the term that's proportional to the error, the D term, which is proportional to the derivative of the error, and the I term, which is proportional to the integral of the error.